Today we're going to solve one optimization problem, but first let's review some geometry. So in 3.9 related rate, we revealed the formula for the volume of cylindrical can. Okay, so so for a cylindrical can that has a base radius of the base to be r and the height to be h. The value here is the base area times height. Base area here is pi r squared. So it is pi r squared times height h, okay? So that was the formula for the volume for this, cylindrical can, okay? Now, what about the surface area? Surface area over here is consists of the top and bottom and also the side, okay? If you use the scissors, okay, think about that. We use the scissors over here and we cut along the side here and open it up, okay? And you're gonna see that the top and bottom will be a circle, okay? And the side, when you open up, okay, it's going to be a rectangle, okay? And for this rectangle, the length of it is equal to the circumference of this circle. So the radius is r, the circumference of a circle is 2 pi r, okay? So this is 2 pi r. The width for this rectangle is a height, so it is h. So when we find the surface area for this, this cylindrical can right here, will be 2 pi r squared, okay, top and bottom, and then also the side will be 2 pi r times h, so it's 2 pi r h. So surface area here will be equal to 2 pi r squared plus, and this is for 2 pi r squared is for the top and bottom, the two circles over here, and then the side will be 2 pi r. It's going to be 2 pi r times h. Okay. So this is a formula for the surface area of this cylindrical can. Okay. Now, in this example 2, okay, a cylindrical can is to be made to hold 1 liter of oil. Okay. Now, you might wonder what is 1 liter, right? This is the liter here is, well, have you ever, well, many of you have seen this soda bottle, okay? You can see that you can buy it in Walmart, okay? Those soda bottles, this big one, okay? This big one there, and they are 2 liter, okay? So there are 2 liter over there. Okay, so 2 liter. Can you turn it on? Okay, so there are 2 liter. Okay, so 1 liter is like half this soda bottle. Okay, so half this soda bottle. Okay, so think about that. Okay, so that's 1 liter. 1 liter also is 1,000 cubic centimeter. Okay. So I also look it up. This is called in Chinese. Okay, right. Okay, so that cylindrical can is to make to hold 1 liter of oil. Okay, this is about half the soda bottle right here. Okay, and we try to find the dimension that will minimize the cost of this the metal. to manufacture the can. Okay, so we want to minimize the cost of the metal. Okay, so well, it doesn't give us a price for the metal. Okay, so in order to minimize the cost of the metal, we want to minimize the surface area for the can, because the surface area is proportional to the cost of the metal. Okay. So the first thing we do here for any wall problem, okay, we try to draw a diagram. Okay, so over here, we draw this diagram right here. Okay, and we want to enter what are given and what is unknown. Okay, so we're given, and we also want to introduce rotation in this diagram. Okay, so I draw this diagram here, and I indicate the radius of the base here to be R, and the height over here to be H. And for the surface area, I use S to stand for that. Okay, the value for this can I use V. Okay, in this case, it's 1,000 cubic centimeter. Okay, and what are we looking for? We're looking for the dimension of this. So the dimension of this consists of radius of the base and also the height. So we try to find the radius and the height of this can right here. Okay. Okay, so now we're going to start solving this. Okay. Remember, the first step in any wall problem is L, is let X be, Y be, etc. So we want to declare the variable. So over here, I'm going to, since I already indicate that in this diagram, so the easier way for me to take care of that is I'm going to let R, H, S, and V be defined as in the diagram above. Okay. And the second step is to have the equation. Okay, remember L, and the second step is E, equation. So the surface area is the one that we try to minimize. Okay, so we want to put it on the left side, and we want to express that in terms of other variable. So we already get this formula here. Surface area equal to 2 pi r squared plus 2rh. So we're going to just write down that. Okay. Now, notice that over here, this S here is, we have two, okay, it's expressed as a function of two independent variables, R and H. Both of them are variable, okay? It's going to, they're going to change, okay? So we have two independent variables, R and H. However, we want to express this as a function of only one single variable, okay? So we had to decide which one to keep. And we want to express one of them in terms of the other. So then we have this surface area is a function of one variable only, okay? So what we do here is we try to relate this radius and the H, okay? So then later on, we can express one of them in terms of the other, okay? So we want to relate. So we're going to relate the radius and H, R and H. Okay, so that we can express the surface area as a function of only one single variable. In this case, I think, okay, let's take a look. Okay, so we can decide later. Okay, now how can we relate this radius and the height, R and H? Well, is there any information we haven't used yet in this problem? This one here, we haven't used it. The value here is 1,000 cubic centimeter, okay? We want to use this instead of the liter because we want to have the unit for the height and the radius. So that's why we want to use cm, okay? Cubic cm here. Okay, so this one we haven't used. So let's make use of that. Well, we already know that the formula for the volume is going to be pi r squared h, right? Okay, so we have pi r squared. So we have pi r squared h. V is equal to pi r squared h. Okay. Now the volume here is 1,000 cubic centimeter. Okay. So 1,000 cubic centimeter equal this. So over here, the R and the H are related. Okay. Now we want to express one in terms of the other. So looks like it's easier to express h in terms of r. Okay, so we isolate the h. H is 1000 divided by pi r squared. Okay. Now we're going to substitute this, put it back in h. Then we come up with this. Okay. Now we're going to simplify it. So here the pi r divide out, and 2 times 1000 is 2000. So we're going to get, okay. So we get this surface area now is expressed as a function of only one single variable, which is this ry here. Okay. Now remember later on, we want to differentiate this to find critical number. So it's better that we write this one in a power form. Okay. So this is 2000 times r to the negative one exponent, yeah, negative 1 power. Okay. So now the next step, once you find this function, is to find the domain for this function. So in this context here, in this example, what will be the r? Okay, r here will go from what number to what number? Okay, so over here, let's think about this. Okay, now when the can is the radius, well, all we know here is the value for the can is 1000 cubic centimeter. Okay, so I can make the radius to be very small, but then I'll increase the height, and it still hold 1 liter, right? So, but the R here cannot be negative and cannot be 0, okay? So R here has to be greater than 0, okay? And also, what happens here if you make the height to be small, okay? When the height is small, then you have to increase this radius. So then it's going to be big enough to hold 1 liter, right? So as this height going smaller and smaller, what happened here is the radius of the base is going to increase, okay, and bigger, okay? So the radius is going to go to infinity as the height going to 0 from the positive side, okay? Okay, all right, so now we see that the domain for this function, the r here, just require that to be greater than 0, okay? So r can go, there's no limit on the r can go up to infinity, okay? So the domain will be, it's going to be from 0 to infinity, not equaling 0, okay? So all positive number, okay? Now, after we find the domain, okay, we're going to find critical number. So we're going to differentiate this function right here, okay? So we're going to differentiate this function, differentiate that is 4 pi r, okay? Differentiate this. The duality r to the negative 1 is negative 1 over r squared. So we found the duality, okay? Now we're going to combine this into one single expression. Okay, so that will using the common denominator r squared. So we got this. Now to find critical number, we're going to see when this first duality equal to 0 and when will this first duality be undefined. Okay, now first duality here equal to 0 when the numerator equals 0 and the denominator does not equal 0. This numerator equal to 0 over here is going to have this pi r cubed minus 500 equals 0. Okay, solving for r is the cube root of 500 divided by pi. And that's in the domain, and that is one critical number. Now, what about if we set the first duality to be, what happened to would the first duality ever be undefined? Well, it is undefined when this denominator equals 0, when r equal to 0, but that is 0 is not in the domain. So 0 is not a critical number. That's not in the domain, okay? So we only get one critical number, which is this one, okay? Now we're going to make a table. So in the table, we will have 3 rows, radius and the first derivative and the function itself, okay? So we use this critical number to divide the whole domain. So we put the critical number in, okay? And then what happened here is it's from 0 to infinity. So this will be 0 to this. And then after that will be from this number to infinity, okay? Now we're going to see the test the sign for the first derivative, okay? I pick a number here, okay, and test it and put it into the first derivative over here, okay? And I come up with negative, okay? And so the sign for the first derivative will be negative over here, and also pick a number here, so it is positive, okay? And over here, at this critical number, the derivative is equal to 0. So when the first derivative is negative, the function is decreasing. When the first derivative is positive, the function is increasing. So over here, as you can see, this function value over here, okay, it's going to be a local mean. Okay, it's going to be a local mean, but it's also going to be the absolute mean because think about this. It's always decreasing on the left and always increasing on the right, on the whole domain, right? So this function value over here, okay, has to be absolute mean. Okay, so that is going to be absolute mean also. And when R is equal to this number right there, okay? Now we found that when R equal to this, we got the absolute mean. So that means the surface area is going to be minimized. We don't need to find the surface area. That was not the question they asked. They asked you to find the dimension. So I find the radius. I also need to find the height. So the height over here, we can substitute this back into this expression here to find the height h. So we're going to get 1000 divided by pi r squared, and 1000 divided by this, that's equal to 2 times this, which is equal to 2 times r. So in other words, that the height for this can right here is going to equal to 2 times the radius, okay? Two times the radius, which is the diameter, okay? And if you do it that way, the surface area for the can is minimized, okay? Now you might wonder, how did I get from this step to this step? So I put a side note over here. 1000 divided by pi of this one square, you know that this is a cube root. And when you square that, if I want to get rid of the cube root, I need to just have to multiply by cube root of 500 divided by pi, because that way this one here is 500 divided by pi to the 2 over the power, and here is 500 divided by pi to the 1 over the power. They multiply and turn out to be 500 divided by pi, okay? So when I multiply this, I also multiply this up here, okay? Multiply this up and down. So down here we have pi times 500 divided by pi, the pi divide out. 1000 divided by 500 is a 2. So we get 2 times this, okay? So that's how I got this, okay? So, and this number turned out to be, it's just the same as the R. So this is 2R, okay? Now, you can see that when you try to minimize the surface area, then this height over here will be the same as the diameter over here. In other words, the cross section here, you can see a square, okay? Analysis actually showed that large can should be almost square like this in order to minimize the cost for the can, okay? So this is an example of a can. The cross section is a square. Now, if you graph this function, the surface area function, the graph is going to look like this. And you see over here, okay, between 0 and 10, this number here is this number, which is about 5.4, okay? Then the surface area is going to be minimum, okay? Right, so notice that what happened over here in this, so this is the end of this solution right there. Okay, so we finished this optimization problem. However, notice that what I did here in this table over here, decreasing on the left, increasing on the right, this number here is the absolute mean, okay? And in the book, they actually give that as the first derivative test for absolute extreme value. So it says that if the first derivative is going to be positive for all x on the left side, so it's going to be increasing on the left, and then over here is negative for all x on the right, so decreasing on the right, then this is going to be the absolute max, okay? And if it's decreasing, okay. So if the function here is, I think the book here has a typo over here, okay? So I just noticed that over here, this should be a negative, should be less than, okay? So that was an error, right? That was a typo right there, okay? So when the first derivative is actually a negative on the left, so the function is decreasing on the left, and then over here, it is positive on the right, so the function is increasing on the right. Then the function value down, so decreasing, increasing. So the function value down here is going to be the absolute minimum, okay? All right, so however, I think we don't need to try to memorize this because once we use a table like this, it is very clear that this is the absolute minimum, right? So that's a good advantage of making a table. It gives you more visual cue of why this one here is the absolute mean, okay? Okay, so I like to organize it using a table, okay? Okay, so now notice that there is one alternative solution to this example. We can use implicit differentiation to solve this problem right there, okay? Notice the surface area is equal to, remember that was 2 pi r squared plus 2 pi r h, okay? And the value for this cylindrical cam here is pi r squared times h, okay? Now we're going to differentiate implicitly with respect to r, okay? So we're going to differentiate this with respect to r. So differentiate this with respect to r, we get s prime, okay? That's the derivative with respect to the derivative of the function s with respect to r, okay? And when I differentiate this with respect to r, I will get 4 pi. So I'm going to get 4 pi r, okay? Now for this part right here, this is a product of, remember r and h both are changing, okay? So they are not constant. So when we differentiate that, think about this, 2 pi r as the first function f, and the h here as the second function g. So this is a product of two functions. So when I differentiate that, I had to use the product rule, okay? So I first differentiate 2 pi r with respect to r, so that's 2 pi h. I'm sorry, that's 2 pi, okay? And then times the second function h, okay? And then plus, now the first function here we copy, so that's 2 pi r, and then times the derivative h with respect to r, and we use h prime right here to indicate that, Okay. Now, similarly for this, we're going to differentiate this with respect to R on both sides. The duality this, we had to also use the product rule because that's a product of, think about this function pi r squared and the function h, okay? So when we use a product rule, we're going to take the duality of this pi r squared with respect to r. So that would be 2 pi r, and then we times h, plus the first function pi r squared times the duality of this with respect to r, which is h prime, okay? And that's equal to the duality of this constant here is h, okay? Now, the minimum is going to occur at, okay, the minimum is going to occur when, at a critical number, okay? So it's going to occur at the critical number. So we're going to set this first duality equal to 0. We're going to set this equal to 0, okay? Now we're going to set that equal to 0. And we're going to divide by 2 pi on both sides. So we end up with this equation, okay? Now this equation over here, we also simplify this by dividing pi r on both sides, okay? And then we're going to get this, okay? This equation right here, okay? Let's call this equation 1, this equation 2. So when we use equation 1, subtracting equation 2, so we end up with 2r, and then minus h minus 2h is minus h, and this will subtract out. So I'm going to end up with 2r minus h equal to 0, and which is the same as h is equal to r. So over here, as we expect right here, so h is equal to r, okay? So that is an alternative way to solve example 2 using implicit differentiation, okay? So that's the end for example 2, okay? Don't forget to do homework, okay? All right, thank you.